Hey guys, in this video I'm going to do a problem in the book, problem 3.39. So just an overview of what the problem is. You can read it in more detail in the book, but we have a student on a train. The train is moving at 10 meters a second, and the student throws a ball at 60 degrees above the horizontal. Professor standing on a nearby hill observes that the ball moves just straight up and down with no horizontal component. The question is, how high does the professor observe the ball to go? So there are two reasons why I would like to do this problem as a video. Number one is that it's more complicated than the example in the text. The example in the text is a little simple. We're going to be testing you on how well you can do the relative velocity problems, but we don't have a lot of time in class. So I thought I would give you an example of a problem which is really harder than what we would ask you, so you can see what these problems are like. In addition, this problem at the end uses a kinematic equation which most of us haven't seen. So we've been using the kinematic equations, but there's a special one which some of you have used, and I've seen you use it, and others of you haven't, and it will simplify your life if you can use this other kinematic equation, which is given in your book in table 2.2. So those are the two main reasons why I want to go into this problem in detail. So first we should try to get a better idea of what's going on in this problem. So we have a train car moving like this at 10 meters per second, a student on the train car, and a professor outside the train car. So the student throws a ball, and the ball travels at 60 degrees above the horizontal in the train's frame of reference, but the professor sees the ball just go up and down. So what happens? So let's first think about what happens if the student threw the ball that way. Well, then the professor would see the ball at a higher velocity than 10 meters per second, and certainly would be moving in the horizontal direction. So that's not what's happening. So let's get rid of that. So what happens if the student throws the ball in the other direction? Well, if the student throws the ball in the other direction at exactly the right velocity, namely if the horizontal velocity right here is the same as 10 meters per second, then it will appear that the ball is stationary in the horizontal direction. This is very much like, when you're at the airport and they have those moving walkways, and you get on the moving walkway and then walk the opposite direction, it appears that you're stationary relative to the airport, although you're walking on the walkway. Well, that's exactly what's happening here. The student throws the ball in that direction, and the horizontal velocity exactly canceled out the other horizontal velocity, and so the professor sees the ball just go up and down. So we could first write that, okay, the velocity of the ball in the x direction is 10 meters per second, maybe negative 10 meters per second if the positive direction is the direction of the motion of the car. But that's not quite good enough for what we want to know. So when you're encountered with a complicated problem like this, it's best to write down exactly what you're trying to find and what you're going to need in order to find it. So what we're trying to find is, how high does the ball go in the professor's frame? So what do you need in order to know that information? Well, we know about projectile motion, so we know that in order to find out how high a ball goes, you need to know the vertical component of the velocity. So what we need to know is the vertical component of the velocity in the professor's frame. Well, so how are we going to find that? The information that we have is the velocity of the car in the professor's frame, and the angle in the student's frame. So that's definitely not enough information to get us there. So what we're going to need to use some information about relative velocities to get us the vertical component of velocity in the professor's frame. So this is sort of our pattern of attack. In order to get to 1, we're going to start with 3. We're going to need to work out some things about the relative velocity. Hopefully that information is going to get us the vertical component of the velocity in the professor's frame, and then hopefully this will lead us, and we know that this is going to lead us to be able to figuring out how high the ball goes in the professor's frame. So first, let's go straight on to looking at the equations for relative velocity. Okay, so here's our basic setup. We have the train car here, we have the velocity of the train car, and here I'm going to start using the book's notation. So this is the velocity of the student, which is attached to the train car, relative to the professor. So if you are the professor, you see the student moving with this velocity. This velocity is the velocity of the ball relative to the student. If you're the student, you see the ball at this velocity, and this is the angle that the ball is being thrown at. And again, we know the ball is going backwards because if it was going forwards, there's no way that the professor could see it only going up and down. That's how we know it's going backwards. So we're going to start out by writing down equation 322 in the textbook. So this is the relative velocity equation, it looks like. In this case, I'm going to put in the right indices for the various relative velocities, and then I'll explain them. So this is the velocity of the ball relative to the professor. And really I chose this because you know the thing we want, remember, is the velocity of the ball with respect to the professor in the y direction. So we're looking for the y component of this. The way that I chose these is that once I have b and p here, this has to be a b and this has to be a p. And the middle ones have to be the same. And so since I have the ball and the professor here, and I only have one other thing in this problem, the student, that's what gives me the exact form of this equation. So now, as with all vector equations, this actually contains two separate equations. So let me write down each of those equations now. So that's the x component of velocity for each of the relative velocities, and that's the y component of velocity for each of the velocities. So let's again think about what we need. We need this in order to do our kinematic equations. So let's see if we can figure out what this side of the equation is. Well, first, this is the velocity of the student relative to the professor in the y direction. But the velocity of the student relative to the professor is only in the x direction, and so that term is automatically 0. Good. So now what do we do with this other term? Well, that's the y component of the ball with respect to the student. So we can just write that out in components. Okay. So now what I've done is I've just used that velocity, and notice that the y component can be found with the sine of theta. So of course I don't know what VBS is, but I've decomposed this now and I have another equation up here. So maybe this other equation can be used to find VBS. So I'm going to break this guy into components and see if I can fill in the rest of this equation. Well, of course, the first thing to notice is that the velocity of the ball with respect to the professor in the x direction is 0, because the ball is only going up and down. So this thing is going to be 0. So that's 0. And then next we want to find the x component of the ball with respect to the student, which is a cosine because we're looking for the horizontal component right there. And so now let's just put in VSP because VSP is only in the x direction. VSP. Okay, now using this, we can solve for VBS. And you'll notice that I made a slight sign mistake here. This guy should be negative because the velocity of the ball is opposite the direction of the positive direction, and I've already said that this is the positive direction, so that has to be a negative sign. So then after we work through this, you can see that VBS is VSP over cosine theta, which is great because now we have this guy right here in terms of two things that we know. And so now we can write an equation for the ball with respect to the professor in the y direction. It is going to be VBS, which we can use here, so I'm just going to plug that straight in. VSP over cosine theta times sine theta, which comes from right there. And of course, because sine over cosine is tangent, we can just rewrite this as VSP is tan theta. So this is what we want in order to move on to our kinematic equation, because we want this for our kinematic equation. VSP is 10 meters per second, tangent of theta, theta is 60 degrees, so we know everything that's in here, and then we can move on to doing kinematics. So I've put our result up in that upper corner, and now we need to talk about kinematics. So there's one very obvious reason why we need to use a kinematic equation which is different from a lot of the ones we've been talking about in class. And that is that there's no time in this problem. There's no explicit time, no time of flight, no partial time of flight, or anything like that. So that means we can't use any equations that have some v naught t's in them or 1/2 at squares in them. We need something else. The second reason is that we need to find the height. So there's a single kinematic equation that not only has no time in it, but also is very convenient when you need to find the height of a projectile. And it comes from, in your textbook, table 2.2 on page 53, and it is the following. the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the y final minus y initial. So I've written this in the vertical direction. It's given in the horizontal direction in your textbook, but of course they're the same. And this satisfies the conditions that we have here, right? There's no time in this equation, and we need to find the height, and that's given exactly by that right there. So now I'm going to write this in terms of the variables we have in our problem. The final velocity is 0 because we're at the top of a projectile. The initial velocity is here. That's the velocity of the ball with respect to the professor, y squared, plus 2 times the acceleration. The acceleration is gravity. It's in the negative direction in this problem, negative g. And the height I'm just going to call h. So that's yf minus yi. So now I'm going to go ahead and solve for h, which is just the velocity of the ball with respect to the professor squared divided by 2g. And then we can sub in our result over here to write the height in our fundamental variables right there. And since this is a very nice result, I'm going to give it a box, which is a universal sign for this is a nice result. And so we can use this to solve our problem. We can plug in 10 meters per second, 60 degrees, 9.8, and it comes out to something like 15.29, I think. That isn't really important. The important thing is to be able to understand how to get to here. So this is the height of the ball with respect to the professor, but obviously one could ask, what about the student? Well, the relative velocity that's happening in this problem is only in the horizontal direction, not in the vertical direction. So that means that whatever velocity the professor sees, since the student is not moving in the vertical direction, the student will see the ball as having the same vertical direction as the professor. So in this case, there's no difference in the vertical direction. And that's because the relative velocity is a vector equation, so if there's any change in the horizontal direction, that's one thing, but that doesn't affect the velocity in the vertical direction. Okay, so that's the end of this problem. Like I said, we will be doing some simpler problems like this on the exam, but we don't have time to cover this in class. I hope that this gives you enough information. It's pretty complicated, but it really is just using the relative velocity equation that's given in the textbook and then combining it with some stuff that we've been doing the whole time, like the kinematics. Do keep in mind this kinematic equation. When you don't have the time explicitly, a lot of you have been doing a two-step solution. The two-step solution is first find the time, and the second step is plug in the time. That's fine, you get the right answer that way, but it's 2 steps. If you know that this kinematic equation exists, you know where to find it on table 2.2, you can go right there every time you have a problem which doesn't have time in it. Okay, thanks guys.